So as I was saying in the last slide, we see that we use heats of hydrogenation to quantify the aromatic stability, and we expect that upon hydrogenation of benzene, we should get negative 360 kilojoules per mole. But interestingly, only negative 208 kilojoules per mole was observed, which suggests that benzene is actually much more stable than expected, right? And the measure by which it is stabilized is known as the resonance stabilization energy. That's called the resonance stabilization energy. Okay, now we'll talk about it. Now, to be able to understand the significant stability of benzene, we need to consider the molecular orbital theory, right? And the interesting thing is that benzene has 6 sp2 hybridized carbons. So each carbon is sp2 hybridized, meaning that it's going to have an unhybridized p orbital. So that means that it's going to be a continuous delocalization of pi electrons, okay, because it is fully conjugated in a ring, and that will lead to continuous delocalization of pi electrons, leading to significant stability. But then that's just one school of thought. The other thing we need to look at is, if you look at the molecular orbital theory, you find that benzene has a total of 6 molecular orbitals, 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals. Now, because it has a total of 6 electrons, if you place all the electrons in the bonding molecular orbitals, you see that the bonding molecular orbitals are filled. They're all filled, and so the molecule is going to be exceptionally stable. So you can see that the bonding molecular orbitals are all filled. And if they're all filled, that means the molecule is going to enjoy significant stability. Now, we don't need to worry about the location of the nodes in you're going to be able to determine the shapes of the molecular orbitals. That's what we will say for the physical chemists. Now, the delocalization of the 6 pi electrons to the 3 bonding molecular orbitals, right, accounts for significant stability of benzene. And you can see, because each carbon has an unhybridized p orbital, the pi electrons are continuously delocalized, and that brings exceptional stability to the molecule. Now, the fact that benzene is fully conjugated doesn't really have much to do with aromatic stability, because as you can see here, cyclobutadiene is fully conjugated. See, it's fully conjugated. It's fully conjugated, but it's not aromatic. You see, cyclooctatriene, tetraene, is also fully conjugated, but it's not fully aromatic. It's not aromatic. See, because interestingly, cyclooctatetraene undergoes addition reactions, see, which benzene does not undergo. See, similarly, you can have 2 units of cyclobutadiene dimerizing to give cyclooctatriene, meaning that they can actually undergo an addition reaction. This is unlike benzene. Benzene does not undergo addition reaction. In fact, it only undergoes substitution reactions. So the question now is, what are the criteria that will make a molecule aromatic? Now, the 2 criteria is, first of all, it must be fully conjugated ring with overlapping p orbitals. That means it has to be planar, because for the p orbitals to continuously overlap, there has to be some kind of planarity. It has to be planar. But the more importantly is that it must meet the Huckel rule which means it must have an odd number of pi electron pairs. So you should have an odd number of pi electron pairs. Okay, and that means that 4n plus 2, right, must be met, where n is the it's a whole number. So the total number of pi electrons should equal 4n plus 2. Or, if you want to look at it in another way, it should have a total of it should have an odd number of pi electron pairs. So it's either the molecule has an odd number of pi electron pairs, or the total number of pi electrons equals 4n plus 2. And we can show that here. Okay, look at cyclobutadiene, you can see that the total number of electrons, which is 4 pi electrons, is not equal to 4n plus 2. How is that? If you take 4n plus 2 equals 4 electrons, right, there's no way you're going to be able to get a whole number. You're not going to get an whole number. In fact, 4 electrons is simply 4n. So that means that it's going to be anti-aromatic because it doesn't have the Huckel number. It doesn't have the Huckel number. Okay. Here you have 8 electrons, which is equal to 4n. So it doesn't have the 4n plus 2 pi electrons. And so again, it is non-aromatic. It is non-aromatic. Now, the reason why this is non-aromatic and this is anti-aromatic is because even though this has a total of 8 electron pairs, 4 electron pairs, which will make it anti-aromatic, it, rather than assume that planar structure, it actually becomes tube-like. And I'm going to explain more about this. But something you need to know, that cyclooctatetraene is not anti-aromatic, rather it's non-aromatic. And we're going to make a distinction between compounds that are aromatic, anti-aromatic, and non-aromatic. But before we go any further, I just want to say something. See, when considering the relative stability of aromatic compounds, aromatic is the most stable. See, and then it's greater in stability than the non-aromatic. Okay, and that is greater in stability than the anti-aromatic. Okay, so even though we expect cyclooctatetraene to be anti-aromatic, but because it wants to become more stable, it assumes a non-aromatic state. See, it assumes a non-aromatic state. Okay, now stability of benzene. If we can explain the Huckel rule using the molecular orbital theory, let's consider the molecular orbitals for, say, cyclobutadiene. Right? Now, cyclobutadiene has a total of 4 molecular orbitals. It has 1 bonding molecular orbital, it has 1 anti-bonding molecular orbital, and 2 non-bonding molecular orbitals. Now, if you put in the electrons according to Horn's, Albaugh's, and Pauli's exclusion principle, you notice that you're going to have 2 unpaired electrons in the non-bonding orbitals, and that is why it becomes anti-aromatic. It becomes extremely unstable, and what it really happens, it tries to dimerize. And that's why we said that if you have 2 units of cyclobutadiene, it's going to exist as a diradical. It's going to exist as a diradical. And basically what's going to happen is that you're going to have electrons flowing like that, electrons flowing like this, electrons flowing like that, electrons flowing like that. And eventually what's going to happen is that you're going to have the formation of this dimerized product, which, as you know, can rearrange this nicely to lead to can rearrange nicely, and you have the formation of this, which behaves as a tube. See, it behaves as a tube. So it behaves as a tube. So you're going to have something like this, something like that. You see? So it behaves as a tube, which is no longer planar. It becomes non-planar. And if it is non-planar, it can never have a continuous delocalization of pi electrons. It cannot, because it's not planar. So it becomes tube-like. Okay? So, even though we expect cyclooctatetraene to be anti-aromatic according to the molecular orbital theory, because if you analyze the molecular orbital energies, you'll find that you're going to have 2 unpaired electrons. Okay, you're going to have 2 unpaired electrons. I'm going to show you how to arrive at the energy levels. Okay, but if we analyze the energy levels for cyclooctatetraene, what we'll see that even though it is supposed to be anti-aromatic, but in practice it's actually non-aromatic. And that's because it assumes a tube-like conformation to avoid being anti-aromatic. Remember, I told you that anti-aromatic is the least stable. So just like the molecule will not want to be the least stable, it wants to enjoy better stability. So it goes from being anti-aromatic to being non-aromatic. See? By assuming this tube-like shape. You see? So you have to see that the molecules actually behave like humans. Just like, remember when we're looking at cyclobutane, rather than being planar, it cannot relieve some of its torsional strain by being puckered. So this molecule again, instead of being anti-aromatic, right, because it's anti-aromatic if it were planar, right, it becomes tube-like, and as a result becomes non-aromatic, right? So the conjugation does not extend around the entire ring. So the system is neither aromatic nor anti-aromatic. See, because it's no longer non-planar. Okay, because it's now non-planar, right? The conjugation doesn't extend around the entire ring. So the system is neither aromatic nor anti-aromatic. And if you're going to look at this molecule here, is the compound below aromatic or anti-aromatic? Of course, if you ignore this center, you kind of see it has 7 electron pairs. And because it has an odd number of electron pairs, right, it's considered to be aromatic. See, it has a total number of electrons, okay, equal to 14, for n plus 2 equals 14, where n, as you can see here, will be equal to 3. So because n is a whole number, then we can say that this molecule is aromatic. It's not anti-aromatic, it's aromatic because it has an odd number of pi electron pairs. Okay, so that's very important. So a compound is aromatic if it has an odd number of electron pairs and at the same time has a continuous delocalization of pi electrons due to a fully conjugated ring system, okay, in which you have continuous overlap of the unhybridized p orbitals. Now, to be able to predict the shapes of the energies of the molecular orbitals, you just have to use the force diagrams to predict it, and it's pretty straightforward. See, pretty straightforward. Okay, you can see these are the different force diagrams. You can see that for cyclobutadiene. You can see the one for cyclopentadiene. You can see the one for benzene. You can see for the one for cycloheptatriene. You can see the one for cyclooctatetraene, right? You can also see the one for cyclotetranoniene, and then you can also see the one for the 10-membered ring and all that stuff. So these are things you need to just remember. Okay, so we're going to talk more about how to determine the different energy diagrams, but for now just get to know more about the force cycles.